In this video, we will show you complete solutions to questions actually 81 through 90. They will show up as 1 through 10 in the numbers that you're actually looking at up here. But remember, this starts with number 81. So our first question was, to balance the equation, you should balance everything but the oxygens. Why? Because the oxygens here are all alone. And when I do that, I come up with this ratio. So with these ratios, it will be impossible to use any whole number as a coefficient with oxygen to balance, because you will have 3 oxygens on the right side over here because the coefficient is 3, and you'll need to balance that with oxygen, which is an even number on the left, and you can't change that subscript. So what you're going to have to do is get just a little bit creative. So let's look at the first balancing. Okay, that comes up like this. Okay, so that's where I got these ratios from. So you have a 2 to 1 to 1 to 3. Now we've got to fix that and make something different. So what are we going to do? In the second balancing, we've got to do something of this nature. First of all, we leave this guy blank because we don't want a 1 there. And look at where all the blue arrows are. These guys are all in balance with each other. That means that this hydrogen is 6, and hydrogens over on this side are 6, because 3 times 2 is 6, and 3 times 2 is 6. The oxygens we don't worry about, remember that. So 2 nitrogens here, because of the 2 as a coefficient, give us 2 nitrogens over here. So these guys are all in balance with each other. What's not balanced is the 3 oxygens with the 2 oxygens. So here we go on our next step. We have to put all that thinking together now and do something like this. In this case, we're multiplying everything by 2. Everything is this 3 by 2 is 6, 1 by 2 is 2, and 2 times 2 is 4. Oops, I missed that. So now the ratio is 4 to 2 to 6, exactly double the ratios that we had here. Again, I'm leaving out oxygen. But now, because I have an even number of oxygens, which is 6, it gets to be very easy to finish off the balancing. And now the oxygen here is going to be 3, and that would give us 2 times this 2 times this 3 is 6, just like this 6 times this 1 is 6. And now we are in balance. And so now we can actually answer the question. It says, when the reaction above, this guy, is completely balanced, the coefficient for ammonia is going to be 4. And so 4 is our correct answer. In this problem, the first thing you need to do is, there we go, come on, let's get this up here. Okay, first thing you need to do is find the molar mass of carbon-12, which is the same isotope as on the periodic chart. So 12 grams of carbon-12 is equal to 12 grams per mole. And so we are going to start with that, with the given. I'm sorry, not with that. We're going to start with the given. So let's go ahead and look at what was given. It says in the problem that how many moles do we have of carbon-12? Where we have 6 grams of carbon-12. Well, there's our 6 grams. And now the next thing we do is turn the molar mass upside down. Why? Because we've got grams on top here and grams on the bottom here. And that is the only way to cancel them out. And then simple division, 6 divided by 12, with the grams canceled out, gives us a total of 0.5 moles of carbon-12. So your answer is letter D. In this question, we're being asked to find atoms So atoms is the find, and grams is the given. So this is going to be 3 fractions total. First fraction we start out with is the 6 grams. Oops, grams. Okay. 6 grams then is our given, and I'm abbreviating given as G. And then the next thing is to figure out the find, which is the atoms. So what are we going to start with? We will start with the given over 1 as normal, and we are going to next try to get grams into moles. For that we have to use the periodic chart and get the molar mass. And what we'll end up with is this little guy. So we've got 1 gram, 98 grams, there we go, 98 grams of platinum, and there's 1 mole of platinum for every 195 grams, which is the number we get off the periodic chart. Now that we have that, our next step is to get into atoms. And for atoms, we use the AVO number. And so next we're going to multiply by, notice moles is on the bottom because moles here is on the top. Grams is on the top here, so grams has to be on the bottom here. So this is what we have. When we multiply all of that out, we get the answer 3.01 times 10 to the 23rd, and that will be answer D. Okay, in this question, our first job is going to be, let me get this little pointer properly oriented. First job is going to be to balance the equation. So, to look at the ratios of the balanced equation, and as we get this one out here, we can see what the ratios are. I think it's important for you to actually look at those ratios separated from the balanced equation, and that kind of helps you go on. Then we are going to circle the 6.02 times 10 to the 23rd, what substance it is, then another 6.02, and so on. Let me show you exactly what I'm talking about. So, first of all, this guy right here, what is that? That's 1 mole. 6.02 times 10 to the 23rd is the definition of a mole. Okay, and that's moles of CO2. Let's use a different color. Now, this guy is also 1 mole, and that guy is water. Now, let's look back at the ratios in the balanced equation. As we look at the meaning of this, that means we have a 1-to-1 ratio of carbon dioxide to water. Is that true? CO2 to water is not 1-to-1, so that rules out automatically. Can't be A. Let's look at the next one. I think you're going to see here this gets easier and easier as you realize what's going on. This guy right here is the CO2, and the number 1.2 times 10 to the 24th is what we get when we multiply 6.02 times 2, and then we have to adjust the exponent to get it back into scientific notation. So this guy right here is going to represent 2 moles. And as we look at the 6.02 times 10 to the 23rd, we already know that that is 1 mole. And now let's see what that is. That is also water. And so is our ratio of carbon dioxide to water, CO2 to water, is it 2 to 1? No, it's 1 to 2. So we've just ruled out our second one. Let's look at this guy. I think you can see where I'm headed here. This is going to give us 2 moles of this guy. Let's go ahead and change that to be consistent with the last guy's in color. And now we look at that as carbon dioxide. Here we go. And then we got this guy, which is 2 moles. for the water. And now we look up here and we see carbon dioxide to water is 2 to 2 in that answer, and it is not 2 to 2. So we have only one answer left, and let's see why that answer works. Just go through the exercise here. We got 6.02, which is 1 mole, and that's carbon dioxide. And then we have the 1.2 times 10 to the 24th, which is 2 moles, and that is water, and is the ratio 1 to 2 of carbon dioxide to water, and carbon dioxide to water is 1 to 2, and that's why our answer is letter D. In this problem, we are being asked, first of all, how many moles of methane are contained in 96.0 grams of methane? So let's first of all look at our given. Our given, of course, is 96 grams of methane. And what are we supposed to find? We're supposed to find how many moles of methane that represents. So we're simply a grams to mole. So first of all, of course, we've got to get our molar mass, and we find that on the periodic chart. And so we know that for carbon, the mass is 12. 4 hydrogens with 1 each from the periodic chart gives us 4, and that gives us a total here of 16 grams. And next we got to get the molar mass of methane, or I'm sorry, next we're going to start our problem. Okay, the problem's going to start with given over 1. And the given over 1, of course, is 96. And next we're going to simply have to use our molar mass calculation. And we know that the molar mass is 16 grams. And because our, here, let's get this guy oriented right. There we go. And because we have grams up here, we have to have grams on the bottom. So the moles is what has to be on top. When you divide that out, you're going to wind up with the problem actually being this very simple calculation, which is 96 divided by 16. And when we divide 96 by 16, we get 6. And so 6.00 moles is our answer. In this problem, we have a given. We want to do given and find in these guys. A given is 13 grams of chromium. And you'll see that guy sitting right here, 13 grams. And the atom, or the element we're talking about, is chromium. Now we've got to do the find, and our find is we're going to atoms. So to get grams to atoms, we've got to take the steps. First of all, we've got to find out here, 13 grams is our given, and that becomes the start of our calculations. Grams, of course, has to be converted to moles. And to get to moles, we have to use the molar mass on the periodic chart. And we find that is 52 grams. 52 grams in the molar mass has to be on bottom because grams is on the top with our given. And the last thing is to simply do the conversion into moles, which uses the AVO number, and that's the 6.02 times 10 to the 23rd. You'll notice that I don't put in the O2. We're trying to keep it simple because that's the way the answers are going to be on the CSTs, and that is going to get us close enough. So what does this problem actually boil down to? The problem actually becomes 78 divided by 52. Where do we get the 78? 13 times 6. And our answer is 1.5 times 10 to the 23rd. And that is going to, you see, when we divided the 52 up here into the 78, or better to say it as 78 divided by 52, you know that number is going to be greater than 1 but less than 2. because 52 times 2 is 104. And when you divide 52 into 78, you know it's going to be more than 1. So it's got to be between 1 and 2. And this is the only answer that fits. And it's got to be closer to the 1.5. Oh, here, this 1.9 is 10 to the 26. So that's way out of there. And we know that because the answer is a 1.5, that the coefficient out here has got to be a 1.5, and that won't change the power of 23. So this guy is way out. This guy is way out because it's a different power of 10. Just using the evaluations, simple evaluations to rule stuff out, lets us solve this one simply. And simple is the name of the game with CSTs. In this problem, again, we're going to have to use a given and a find. So let's do the given first of all. We know that because right up in the problem itself, it shows us that we've got 9.03 times 10 to the 23rd molecules. Okay, we're trying to get molecules to moles, so this would be a relatively simple problem. Again, you want to use your file dump stuff to get this. You know that molecules to moles is only one step. So let's start with the given. Given is molecules, and the next thing is to use the OVO to get us the transition into moles. And since molecules is on the top up here, it has to be on the bottom down here, and the number we're going to end up with will wind up canceling this 10 to the 23 against this 10 to the 23. So the problem in this case is actually boiling down to, come on, open up for me please. There we go. 9 divided by 6. And that's pretty easy. We're going to come up with an answer that is equal to 1.5 moles, which is letter B. Okay, in this problem, again, we're going to have to put our heads on straight by doing the given and find so we know what we're doing. In this reaction, how many grams of iron 3 oxide are required to completely react with 84 grams of the carbon dioxide? So we're going to do given, and given is 84. Okay, the 84 grams comes from here, and we're talking about carbon monoxide. And then right here, the find is, so where does that find come from? Find comes from right here. In this reaction, how many grams? Okay, and oops, I didn't put the grams in there. Let's go ahead and fix that up right now, because this is definitely grams. So it's a question mark, how many grams of Fe. So we're going grams to moles to moles to grams. So that's going to be a long calculation, but the numbers are going to wind up being simple. So we start, first of all, we've got to know what our molar masses are, and that's how we're going to calculate the molar mass of carbon monoxide. And then we also have to calculate the molar mass of iron 3 oxide. So we're going to go and now start with our given. And so the given is 84 grams of carbon monoxide over 1. As we would always do, we put the given over 1. And next we've got our molar mass. This time the molar mass of carbon monoxide, which comes from this calculation. And next we're going to have the molar mass of, or not the molar mass, but the mole ratio. Now, you'll notice up here that I've set the mole ratios for you with this bracket, and that's where these numbers are coming from. And so what we're going to do next is get our moles of iron 3 oxide, and to get that we use the molar mass that we calculated earlier, and that gives us this number. And so the whole problem is boiling down to this very simple calculation. On the bottom here, we have a 3 and a 28, which are multiplied by each other, so that gives us an 84. And notice that that 84 from the bottom will cancel this 84 right here, leaving us 160 as our answer, which makes this guy really simple, and our answer will be right here as letter C. Okay, in this problem, we are going to have to do given and find, and that will keep our head on straight. First of all, in the problem, we are given the, come on, let's get here, Errol. We are given the 54 grams of water. Okay, that came from right here. You'll notice as I write it this way, it gets less lost in the wording like it does up here. And then our find is going to be how many grams of ammonia. And ammonia, of course, is this guy right here. So with 54 grams of water and all of the magnesium nitride that we need, we're going to be able to figure out the exact amount of ammonia that can be produced. So, first of all, we've got to get molar masses again, don't we? Or, well, yeah, we will get molar masses. But at any rate, let's start with the given of water over 1. And next, we're going to go to the calculation that will get water into moles. And when we do that, the 18 grams of water comes from 2 hydrogens and 1 oxygen. The oxygen being 16 and the water being a total of 2. And the next thing off is to use our mole ratio, and mole ratio that we're after is the ratio of ammonia to water. So ammonia is right here, water here, a 6:2 ratio, which I reduced to a 3:1 ratio. And water has to be on the bottom because water's on the top here. So as we go into our next step, after the mole ratio out of the balanced equation, and let's just kind of make sure we get that straight here. We got ammonia and we got water, and those are the guys that we're comparing. And while I'm at it, let's fix up those subscripts. So now that subscript looks a little better. But again, the ratio there, and that's what we're doing here is the mole ratio. Next, we've got to get our mole ratio. After the mole ratio is established, we know how many moles of ammonia we need, and our next step needs to be to get that by using the molar mass of ammonia. Nitrogen, you take his molar mass plus 3 hydrogens, okay, and that is going to give you a total of 17. Okay, 14 for the nitrogen and 3 for the hydrogens. And that gets us our final setup. And what is this problem boiling down to? On top, I'm going to cancel the 17 with the 18 on the bottom. Okay, the 17 from here and the 18 from here. And so what is this problem actually boiling down to? We can divide the 54 by the 3, and or you could use a 4. It's not going to matter that much. And the answer that you're going to come up with is, and for some reason in the answer over here, which is letter D, okay, they didn't put the grams in, and so I'll just put that in right now. And that's grams of what? That's right, ammonia, NH3. And that's our final answer on that one. So, this is the last of the questions for the CSTs that come off of the release questions. And the 10 refers to number 90, of course. This guy, again, is going to require a given and find. If we don't do a given and find, our chances of getting this question right are just about 0. And so what we want to do is establish that the 5.4 grams of aluminum, which is coming from, where is it? Grams of aluminum. There we go. Okay. Mass of 5.4 grams of aluminum. You see that doesn't stand out quite as nicely as this does. And then we're looking for grams of copper. And that's what this all means here in this sentence. So we've got our given and find established. Let's go ahead and start with the given, as always. We're going to have to get those grams into moles. And for that, we look on the periodic chart, and we see that the molar mass for aluminum is 27. So that's a pretty simple thing to set up right there. Our next thing to set up is going to be the mole ratio. And since we're going from grams of aluminum to grams of copper, okay, we've got the aluminum to copper ratio that we're going to be using for the mole ratio. So that's why we get that 3 to 2. 3 coppers on the top because aluminum has to be on the bottom to cancel the moles of aluminum up here. So here's our mole ratio from the balanced equation, which is what causes this to be a stoichiometry problem. And the last thing we want to do is get our moles of copper into grams of copper so we can get what we've been asked for. And let's get this guy to, come on, be nice to him. There we go. And copper on the periodic chart is a 64 grams per mole. Moles on the bottom because these moles are on the top. And so as we go to the end of this problem, here's what it's actually boiling down to. This problem is 5.4 divided by 54. And where did we hit that? We have a 0.1 times 3. Okay, why is it 0.1 times 3? Because there's so many ways to do this. Just a second. So the 5.4 divided by 54, where is that coming from? Well, 2 times 7 is 54, is it not? And so that 54 that we get from multiplying these two, which takes all the numbers off the bottom except 54, 54 into 5.4 gives us the 0.1. Now all we have is the 3 and the 64 left. So it's 0.1 times 3, which is very easy. That's just a 0.3 times 64. And so I think all of you can do a 0.3 times 64 and come up with the 19.2. And 19.2, because it is an estimate, is going to be closest to the letter C, and that's why you'll see letter C in my key. And that's it for the rest of the CSTs. Save it.